Good evening, everyone. As part of our Colloquium lab, we are presenting our presentation on flexible IP address that is also known as flexible IP. And further, we would be suggesting an efficient addressing scheme for the same. Now, let us first understand what actually is flexible IP and most importantly, its need is. Conventional IP address scheme like IPv4 and IPv6 is designed with fixed length, that is 32 bits for IPv4 and 128 bits for IPv6. Thus, it lacks in extensibility as well as transmission efficiency. As the internet world is rapidly expanding, more and more new application requirements are emerging and traditional IP addressing system is not capable to handle that. On one hand, as network is expanding towards Internet of Things (IoT), demand for address length in different scenarios can vary drastically. In case of IoT devices, short address or device ID is more preferable than an IPv6 address for better efficiency coming from less query time. This clearly shows that although IPv6 has theoretically enough addresses, but the actual addresses assignment efficiency is quite low in IPv6. Flexible IP or Flex IP provides an alternative by suggesting a variable length IP addressing scheme that would result in flexibility as it would be flexible enough to adapt to various networks and at the same time will resolve the problem of low transmission efficiency. But due to variable length of flexible IP, conventional routing addressing scheme based on lookup table cannot be used in case of flexible IP. Now let us look at certain parameter on which flexible IP performs better than the traditional IP addressing. In traditional IPv6 or IPv4 addressing scheme, addresses are stored in routing table with data of fixed length so that routers can achieve efficient mask matching and addressing. But at the same time, it costs us huge space and create great challenge in lookup performance. Apart from this, other parameter like throughput, jitter, end-to-end delay, and packet delivery ratio are also taken into consideration in IP addressing scheme. IPv6 supports a large number of addresses, but at the same time it lacks in PDR as compared to IPv4 structure. All these things suggest that flexible IP should be introduced to resolve the problem of variable length addressing. Now, my friend Zad will continue further and will tell you how flexible lookup scheme is implemented in traditional addressing and what's its alternative in flexible IP.
So thank you, Fez. So as Fez talked about how the need of Flex IP and how the conventional IPv4 and IPv6 are leading to less efficiency and transmission overheads. Now let's look upon the traditional IP addressing schemes. So the first route lookup scheme we are going to look is the trie-based route lookup. A trie is an efficient information retrieval data structure used in various scenarios, especially in auto-completing tasks. The search complexity is optimized and they are easy to implement. Tries, however, suffer from large memory access while searching. As we can see from the above figure, that as the length of the prefix increases, as in the example of P4 and P5, we see that the depth of the trie traversed increases. Thus the queried performance is dependent on the length of the IP addresses and thus leads to less efficiency. The second lookup scheme is based on hardware-based route lookups. The scheme reduces the complexity of finding longest prefix match to just prefix match, but still it is not widely accepted due to cost constraints and power consumption issues. Now let's discuss upon the Bloom filters. So Bloom filter is essentially a probabilistic data structure that uses hash maps, those H1, H2, and a vector V of m bits. Invented by Burt and Bloom in 1970, the Bloom filter is a method of representing a set A of n elements The basic idea, as shown in the above figure, is to allocate a vector v of m bits, all initially set to 0, and choose k independent hash functions h1, h2, h3 and so on to hk. And for each output of the hash function, we check bits at that position in the v bit vector. If any of them is 0, then certainly b is not in set A. Otherwise, we conclude that b is in the set, but with a certain probability that we are wrong due to certain number of collisions. This is called as a false positive. Now let's see how it is calculated. The probability that a bit is set is given by 1 over m, and the probability that a given bit is not set or is 0 is 1 minus 1 over m. The probability that a particular bit is still 0 is after exactly passing through k hash functions for a set of n elements can be given by 1 minus 1 over m to the power k into n. Thus we can see that the false positive in this situation is 1 minus 1 over m to the power kn whole to the power k, which can be approximated for an optimal value of k obtained by differentiating this expression, where we find k equals to m by n log 2, and this can be the false positive in this case. Furthermore, to avoid the calculation overheads in the Bloom filter, we are currently reviewing the literatures on one hashing Bloom filter. The one hashing Bloom filter basically harnesses only one base hash function along with certain operators. However, the OHPA for the one hash base function also shows the same false positive probability as that of the Bloom filter. These were the references we reviewed and passed on to our literature, and thank you.